Our presentation this morning is with Aluel Go, who's a specialist at Michigan State University, and he's going to be talking this morning on dairy ventilation or ventilation in general, manure systems, and a little bit about fuel switching, I believe. So with that, I'm going to turn it over to Al. Al, are you there? Al, we can't hear you.
Sorry there. Are we okay now?
Yep. Why don't you go ahead and start over?
Okay, let's start over. I'll start with page 1 here. Dairy ventilation, okay? Basically, it provides for a comfortable environment for healthy and productive cows. Cows continuously produce heat and moisture, and the purpose of a good ventilation system is to remove that heat and moisture from the housing facility, okay? So, this exchange basically occurs whether the temperature is cold in the dead of winter or when it's hot in the middle of summer. The most basic natural ventilation system requires the following items: air exchange, control, flexibility, good barn construction, and ventilation system. The value and importance of providing a comfortable environment for high-producing dairy cows is demonstrated by expanding use of air circulation and other cooling methods. Cows in general are cold weather animals, and basically when relative humidity reaches around 72 degrees or 72%, dairy cows start feeling a mild heat stress. This heat stress is increased at 80% relative humidity and really gets severe at 90% relative humidity. The effects of heat stress on dairy cows has been well documented and includes reduction of feed intake, drop in milk production by 20 to 30%, increased susceptibility to mastitis and other diseases, reduced conception rates, and other reproductive problems. The graph presented before you basically is a graph that charts milk production with regards to air temperature. Okay, so another rule of thumb in terms of measuring when maybe to turn on your fans or increase ventilation is temperature. However, relative humidity is a more accurate rule of thumb measurement. But if you use temperature, the general range in which cows have maximum production is between around 41 degrees Fahrenheit to around 70 degrees Fahrenheit. Again, most cows are comfortable and can maintain high levels of productivity between 41 and 70 degrees Fahrenheit if the relative humidity is not too high. Cows are much more tolerant of temperatures below the optimum range than above, so they basically are still productive at temperatures far below 20 degrees, below 20 degrees Fahrenheit. They are kept dry and sheltered from the wind. Most wintertime productivity problems are the results of animals being shut inside poorly ventilated barns rather than cold facilities. As you notice in the pictures, farmers will tell you when the cows are comfortable, they usually lay down in their stalls. If they are not comfortable, especially during summertime, they will be standing up and not be laying down. One production myth is that since dairy cows are cold weather animals, it is natural for milk production to drop during the summer months when it's very hot. Okay, the chart you have here is of an actual dairy farm that basically has shown that no, you can increase milk production even during the hot winter months. However, this operation has a very extensive ventilation system, and they use it very well as they monitor temperature and humidity in their facilities. So it has this automated system, and it really can push the moist, hot air outside the facilities and bring in cooler, drier air. So you can increase production even during summer months.
Hey, Al?
Yes?
Your voice quality is breaking up. Are you on the phone or over the...
No, I'm on a mic.
Okay.
So unless our system here is...
it was breaking up a little
been
bit.
using the same system we had before, so same computer, so I was hoping this would be okay. Is it still breaking up right now?
Yeah, it's the voice quality isn't real good.
Let me try the phone then. Could you give me the phone number to call in?
Yeah. It's 608-237-5850.
Okay, just a minute.
And you'll need a code. It's 870-3495.
Was it 870?
870-3495.
Do I hit the pound?
Yep.
Okay.
Hello, can you hear me now?
Yep, you have to shut the other one off.
It's off. Okay. Is that better, Scott?
Yep.
Okay, you want me to go back a few slides?
No, you can keep going.
Okay. Basically, I wanted to show this graph to show the basic myth of summer production in dairy. The standard assumption is that dairy milk production goes down during the hot summer months, primarily because cows are stressed and primarily because cows are supposed to be cold weather animals. This actual production chart shows that now dairy milk production can increase during the summer with adequate and well-controlled ventilation systems. Now, I show my trainees this slide because they always see the advertisements where it shows California cows are the happy cows. I think you've seen some of those. Well, I basically tell them that everybody knows that happy cows love cold weather. So this commercial was filmed in the Midwest and not in California. So just wanted to emphasize that cows are really cold weather animals. Dairy ventilation is also to make sure that folks that are working on the operations are comfy as well, okay? A lot of the milking parlors, as well as the areas where workers are working most of the time, need to be properly ventilated and aerated as well. To maintain and increase milk production levels, a greater number of dairy farms are implementing options to mitigate the effects of heat stress. The energy used by these systems to provide air circulation, ventilation, evaporative cooling effects represent an increasing portion of the aggregate electrical energy consumed. The rapid growth of cow comfort systems on dairy farms has occurred because of the magnitude of economic benefits that can be achieved. It is worthwhile to consider the energy management opportunities that exist for these systems. To reduce the effects of heat stress on dairy cows, a variety of measures have been developed, and these include natural ventilation, shading, circulation fans, and circulation fans with evaporated cooling systems, or as some would call them, misters. To show you the impact of energy used for ventilations, I basically have three charts here from 3 states. In New York, the ventilation average is around 19% of their energy cost, electrical energy cost. In Wisconsin, ventilation covers around 22% of that energy cost. Here in Michigan, this was a little surprising from the data we got. We're usually only using 8%, and I tried to find out pretty much and looked at the average temperatures and basically found out that in Michigan we have an insulating effect by the Great Lakes, and we are about 10 degrees warmer during the winter as well as 10 degrees cooler during the summer. So that could be the reason why our ventilation percentage is a bit down from the 2 other states. The first is natural ventilation. Natural ventilation of dairy housing structures is accomplished by building high-sided open facilities oriented to take advantage of prevailing winds. If the building has a peaked roof, an open ridge provides a natural outlet to allow warm air to rapidly exit the building. Proper orientation of the building so that prevailing winds blow through the structure from one side to the other helps reduce temperatures for livestock housed within. That's during the summer months. The advantage of natural ventilation system is there is no energy input. The major disadvantage is that when there is no wind, there is little or no air circulation or cooling effect within the structure. In large facilities, most of the natural ventilation occurs through the roof, through the ridge openings, and through the side for side openings. I will show you basically, the next slide, 2 major ridge styles. We have the conventional design as well as the California design. Just wanted to show you, this is basically just an open roof here. The opening here is on the side for the California design. One disadvantage with the conventional design is if it rains, you'll have a wet spot right in the middle. So those are the 2 major ridge vent designs. The slides here shows you some dairy facilities which have a combination. This picture here has an open vent, and these ones here have covered ridge vents as well as this one. But if you go around and see these freestall barns, you can see various styles of ridge vents, and some call them also barn eaves. We also have openings in the side. If you notice here, that's another way for natural ventilation to occur on a dairy farm facility. Some of these sides have manual curtains or panels. If you notice here, this is a cow racing barn here, and they put panels here during the winter, and they remove them during summer for openings. Some facilities have automated barn curtains. I have a link here on the site. When you pull down the attachment or the handout there for this presentation, brings you to a little video that shows you how these automated barn curtains are used and how they work. Another strategy is shading. It's very simple. Structures with flat roofs or shade cloth covers provide a place for dairy cattle to get out of the direct sun. The shade structure just casts a shadow in response to the movement of the sun throughout the day. The cows are free to move within the shaded zone as the day progresses. Shading systems like natural ventilation systems do not require any input of energy, okay, unless they're supplemented by mechanical air moving systems or misting systems as well. Another system which is more common, or the most common system basically, is circulation fan systems. The major users of electrical energy in circulation fan systems are the electric motors used to drive various configuration of fans and fan blades. Experts agree that the heat stress in dairy cows begin when the ambient temperature reaches between 65 to 70 degrees Fahrenheit and relative humidity is 40% or higher. It is normally recommended that circulation fans should be turned on when temperatures reach 70 degrees Fahrenheit in order to keep cows within their comfort zone. A lot of farmers will try to save energy and not turn on their fans, but basically data that we've gathered shows that the amount of energy they are using for those fans will be recouped, and they will even get much more over their cost by the increased production during those hot days or hot periods. So at this point, we are seeing that turning those fans on really pays off. Circulation fan systems include several different types. All circulation fans common to dairy housing systems are axial flow propeller fans. They have either flat, teardrop, or airfoil-shaped blades attached directly to a motor or to a motor and belt drive system. Most circulatory fans, except the basket style, are mounted in a circular ring to help control airflow through the fan. Now, some farmers will tell you that they prefer belt-driven fans, and I wanted to ask why that was so, since belt-driven fans are usually a bit less energy efficient than the direct motor fans, and basically said they are having a better experience with being able to maintain them. So that's just an opinion of some farmers, but in general, belt-driven fans are usually less efficient. Overall fan efficiencies vary greatly, and performance is affected by numerous factors, including types of blade, clearance between the blade tip and the fan housing or orifice, the design of the fan housing and orifice panel, speed at which the fan operates, and any obstruction to airflow, including fan screens, guards, shutters, motor drive, etc. One aspect that fans provide is they move air, and a lot of farmers will tell you, and there are other resources and reference that basically say if the air movement in, let's say, a freestall barn is between 4 to 5 miles per hour, This prevents flies and other insects that usually bother and pester cows from landing on them. So therefore, with airflow speed at this level, it provides a better environment for cows, since they're not bothered that much with flies, especially the biting flies. The 6 major types of fans, as you can see here, we start out with what we call a basket fan. It has kind of a fan covered with a mesh, wire mesh. You have a box fan. You have a panel fan. We see a lot of these types of fans here in Michigan and surrounding states. We have funnel fan, and we have 2 examples of example here of large, low volume, high speed fan, as well as a low volume, low speed fans. These big fans here are also called paddle fans, as most manufacturers call them. Some of the efficiency ratings or category of these fans are presented on the table that you've seen here. As you can see here, the basket fans have the lowest operating efficiency level. The high volume, low speed fans have the highest general operating efficiency level. And most of them are in the moderate, and box fans can be from moderate to high. So this is, as a general rule of thumb, the energy efficiency levels of the various types of fans. As you can see in this picture here, we have panel fans that are being used here. We also have open sides, and I believe they use manual curtains for these sides. The ends are also opened out. So basically this facility uses a lot of natural ventilation from the sides and from the ends, as well as from the fans. And this also has a ridge vent over this side. We just couldn't see it, so the design of this facility is pretty effective in terms of providing a cool, dry facility for dairy cows. Here are other examples. Fans or circular motors are mounted over cows' backs to keep them cool. Also in the holding area, we have fans to keep them cool as well. So these are some of the areas where fans are being utilized. Fans are also utilized in the milking parlor itself to help cool that area for those that are milking the cows. Some folks have calf housing, and they have these panels they put up during winter. They remove these panels during summer. Here is the operator basically in the process of putting these panels up. And each stall for the calves have also fans that bring in outside air. Another type of ventilation system is what we call tunnel ventilation system. Basically, these fans, they are relatively large fans, are put on one end of the facility, and basically either you can change the direction to either blowing air through the facility from one end or another, or at times reversing the fans and sucking the air out from one end to another. So these are another type of ventilation systems that you may see out there in dairy facilities. Some systems are a combination of circulation fan systems with evaporative cooling. A dairy cow produces a large amount of heat, but she is not very efficient at dissipating that heat at temperatures above 70 degrees Fahrenheit. If the temperatures are 60 degrees Fahrenheit or below, a cow can dissipate excess body heat through convective, conductive, and radiant heat transfer from the skin. However, at higher temperatures, above 70 degrees Fahrenheit, cows have to increase heat dissipation by panting. As a cow pants, she increases her breathing rate, thus increasing airflow through her lungs. Evaporative and convective heat transfer moves heat from her body in the exhaled air. However, only about 20% of the excess body heat can be dissipated this way. At high temperatures above 90 degrees Fahrenheit, which commonly occurs during the summer months in the Midwest, air circulation needs to be supplemented with evaporative cooling to keep cows comfortable. Now, not all farms need evaporative cooling or misters, but some barns and some facilities that are not designed as well do need this, okay? Evaporative cooling in dairy resting barns uses the cooling effects of rapid airflow and circulatory fans along with the cooling effects of evaporating water. There are two common types of systems used to provide cooling water. You have the low-pressure sprinklers and high-pressure misters. Fan maintenance, okay? Basically, dairy ventilation circulation system requires scheduled maintenance. Poor maintenance can reduce fan efficiency by as much as 40%. Cleaning of fan parts, especially the blades, can improve long-term efficiency. Accumulation of as little as 1/8 inch of dirt on the fan blades can significantly reduce fan performance. Proper lubrication of bearings and other moving parts will keep performance level high and reduce energy. In reality, we all know, though, that if you go into a dairy farm, maintenance of fans is not a high priority. I mean, dairy farmers have a lot more important things to do. But if you can explain to them that there is a benefit for maintaining and cleaning fans, hopefully they could develop a regular maintenance system that they can follow. Also, bent and damaged or misaligned fan blades should be repaired or replaced since they cause an imbalance and reduce fan life and performance. Repairing or replacing the fan blade is far less costly than repairing or purchasing a new fan. Some of the recommended monthly fan maintenance procedures are, first of all, disconnect the power, remove all dust accumulated on the controls and motors, as well as remove dust and buildup on the fan blades, fan housings, shutters and guards, lubricate all pivot points of shutters, as well as if the motor is not sealed, some of the areas where you can lubricate. Check all wiring for from the service panels to make sure there are no damaged wiring components. For fan belt-driven fans, make sure the pulleys are properly aligned and the belt has proper tension. Okay, replace any worn belts. Reattach all guards before turning power back on. If fans are thermostatically controlled, compare the thermostat with a reliable thermometer. So these are some of the things that you could do to make sure your fans are maintain their efficiency for a much longer lifespan. Now, some of the problems cannot be seen visually directly. This is an example of a paddle fan right here, and which we took an infrared camera and took a picture of it because we were suspecting something was not quite working with this fan, and we noticed that this fan was operating at a much higher temperature levels than the other fans, and we finally found out that there was a small leak on this fan. So these are some of the tools that an auditor or somebody who's looking at doing an energy efficiency assessment of their of their farm can use in terms of looking in greater detail into their fans. This is the fan that had a little leak, very bright light that shows it was operating at a very high temperature, compared to the other fan that was not as hot and was operating at a much lower temperature. So this is an example of fans operating at different temperatures with one leaking a little bit of oil. Selecting fans, okay? To compare fans from different manufacturers, the Bioenvironmental and Structural System Lab, this is called short for BESS, at the University of Illinois at Urbana-Champaign, conducts standardized tests on fans with accessories and publishes the test results. Selecting fans for energy efficiency, simply expressed at flow rate per unit of input energy, or CFM per watt, is becoming very important. A higher CFM per watt rating will indicate a more efficient fan. Remember that both fan performance and energy efficiency can vary widely. For an example, a 48-inch fan can have an efficiency as low as 13 CFM per watt or as high as 23 CFM per watt at 0.01 static water pressure for the same application. This is why it is recommended to review testing information from the BESS. When comparing fans of different sizes or from different manufacturers, it is very useful to study their rated performance data and to find out if the evaluations have been tested under conditions similar to those in your facility. In addition, BESS have identified important fan selection criteria. They are quantity of air that must be moved at different static pressures, energy efficiency comparison among fans, quality of dealer service and support, reliability and life of fans, suitability for intended application, and cost. One thing I'd just like to point out here, that actually this is a duplicate slide, so I'll just move on. Barn ventilation tips. Reducing ventilation in a naturally ventilated dairy barn during frigid winter weather might seem like a good way to keep the barn warm, but this strategy could be a disaster. Some dairy producers who have insulated, naturally ventilated freestall barns are thinking about tightening them up, reducing the cracks, reducing some of the spaces between panels or walls or ceilings, okay? Closing the eaves, inlets to keep the barns warmer. The barns may seem too cold and drafty for the cows. However, barns of this type are designed to be cold within a few degrees of the outside air. Closing eave inlets will create wet, damp conditions and lead possibly to respiratory health problems for the cows. Wet, damp conditions will be evidenced by fog, condensation, or frost on building surfaces, and of course, high humidity. At 30 degrees Fahrenheit, an 1,100-pound dairy cow will give off about 20 pounds of water vapor per day through respiration and losses through their skin as sweat. This moisture must be removed by venting air. It can take a venting rate of around 170 cubic feet per minute per cow to remove it. Closing eave inlets restrict the ventilation rate, and causes moisture to accumulate in the barn. As moisture accumulates, it will begin to condense as cold surface as cold surfaces. And if the surfaces are below freezing, frost will form. In addition here, in severe cold weather and during blizzard conditions, eave inlets can be partially closed to reduce airflow and the amount of snow blowing into the barn. According to the Midwest Plant Service, the minimum inlet opening during severe cold weather is 1/2 inch for every 10 feet of building width. There should be, note here, there should be an inlet on each long side of the building. When normal winter weather returns, eave inlets should be reopened to the standard 1 inch per 10 feet on both sides of the building. Cows need a dry, draft-free resting area. Drafty conditions at cow level can be reduced by patching curtain holes, minimizing gaps at the ends of the curtains, and sealing around doors to eliminate small wind gaps when extreme wind and extreme low temperatures occur. Avoid the temptation to keep uninsulated, naturally ventilated freestall barns too warm. They were designed to be cold, and dairy cows do quite well in cold temperatures when they are dry, protected from the wind, and properly fed and watered. I wanted to note that some of these comments are from Kevin Yanni from the University of Minnesota Extension. Oops, I did that. Ventilating summary. Box-type fans and large, low-speed paddle-type fans are often called high-volume, low-speed, or HVLS fans, are the two principal types used for animal housing. Box fans are used in conventional tie-stall barns or loose housing such as freestall barns. The HVLS fans are recommended only for loose housing applications with high side wall heights. If fans are being used, choose the most efficient ones available and make sure they're equipped with totally enclosed motors. Generally, as fan diameter increases, the efficiency also goes up. For example, a standard 48-inch box fan would have an average efficiency around 17 CFM per watt, while a high-efficiency 48 box fans will move 20 CFM per watt or more, a 20% increase in efficiency. I think we have a typo here. I apologize. This is the first one is a comparison between a 36-inch box fan compared to a 48-inch box fan. While high-volume, low-speed fans are normally recommended for loose housing applications, they may still be considered for modern and open freestall facilities. Keeping a fan in good repair is as important in reducing energy costs as buying the most efficient model. Poor maintenance can reduce a fan's efficiency by 50% or more. For fans that are belt-driven, belt adjustment is the single biggest maintenance problem with certain types of fans. Belt-driven fans must be regularly adjusted through the hot season for full air movement, so they should be easy to adjust. When the fan is on, louvers must be fully open, otherwise they will restrict the flow of air from the building. A restricted fan operates longer and bears a heavier load to achieve the desired amount of cooling, which costs more in electricity. Installing thermostats to control the fan's on and off operation saves energy and increases productivity. Research has indicated that dairy cows begin to show heat stress at around 74 degrees Fahrenheit with 70% relative humidity. Okay? So it is recommended that the thermostat be set between 70 and 75 degrees Fahrenheit. Use thermostats designed for outdoors in damp, dusty conditions. Mounting the thermostat out of the reach of animals, but in an area that will accurately reflect air temperatures, around the livestock. To ensure accurate readings, the thermostats need to be protected from direct sunlight and checked, cleaned, and perhaps recalibrated monthly, since dust can also affect accuracy. That's basically for fans. Now, I'd like to segue into manure systems, okay? Manure handling. All dairy farms produce and then must dispose of waste products from two major sources: the wastewater from their milking centers and the waste products from digestion and other bodily process of dairy cows. A significant amount of energy is used basically, especially in California, where they have a higher level of environmental regulations. They use a lot of energy and systems to take care of this waste, as well as milk water, wastewater. So the source of basically waste and manure is basically washing of milking equipment, cow prep wash pans, backflush of milking equipment, and parlor and holding area flushing of manure. There are 4 types of manure collecting systems employed on dairy farms. Flushing systems utilize water to dilute and transport manure, automatic alley scrapers, vacuum-operated collection equipment, tractor or skid steer manure scrapers. An example here is pretty much a tractor driven skid blade that basically skids and just scrapes the manure from the center aisle here. That's one example. The chart that's presented here gives you an idea of pretty much how much, or a general indication of how much manure is produced for lactating dairy cows. Okay, as production, your production level increases per dairy cow, the amount of manure also goes up. So, as we note here at the lower axis here, as you increase the production level per year of your dairy cows, the amount of manure produced also goes up. So this is kind of like a guide for you to use to try to see the amount of manure being produced on a farm. There are various manure systems. This system here is a flush system, and the water is usually put in a pumping system. The pumping system has a filter, and what it does, it reuses the water and flushes the facility again. So basically, they are reusing the water and using a filter system to kind of clean up the water to reuse. This is just basically an open lagoon where some of the waste is being stored. Some of the lagoons have filters or have film on the sides. Some of the lagoons do not. So the variation in terms of the size, complexity of this manure lagoons vary quite a bit. Manure is spread in the field several ways. This is an example of injecting the manure into the soil, which is pretty much the most efficient way in terms of retaining the nitrogen content of the manure. Some are just stored here and then spread out into the field. Usually this system is done sometimes for daily haul dairy spreading. Be careful though, there are restrictions in application of manure in some states with regard to winter regulations, with regards to offsets from waterways, as well as regulation in terms of applying manure in fields with high phosphorus content. So those regulations impact your manure system and how you dispose of your manure in the field as well. Now, estimated nitrogen losses. Now, I focus on nitrogen because it's one of the more expensive elements that farmers use to augment the natural occurring nutrients in their field for growing crops. As you notice at the bottom, the lagoon system, which is very common here in the Midwest, you lose 70 to 85% of the nitrogen in the manure. Now, I'd like to highlight that because we want to give you kind of like an impact and value of that later on. So these are kind of describes the various systems and their various storage facilities and the nitrogen lost given those storage facilities. The bottom line, nitrogen is too valuable to lose as a crop nutrient, as well as it impacts air pollutants, and as an energy efficiency asset. It has been calculated that to produce 1 pound of nitrogen requires equivalent of 11 gallons of diesel in terms of energy use. That covers production, any manufacturing aspects, transportation, packaging, and as well as delivery. It is worth time to calculate the savings that can be realized by making a management change. For example, giving the example of 1 pound of nitrogen or 5 pounds of diesel, if you can reduce your nitrogen input, let's say in a corn operation, from 140 pounds nitrogen to 120, that's a saving around 20 pounds of nitrogen per acre. That's equivalent to 500 gallons of diesel in terms of total energy cost. Now, nitrogen around 70 cents per pound, that's around $14 savings per acre. So making good use of the manure and the nitrogen in the manure that's coming from your dairy animals has a great deal of value. Basically, manure management covers collecting and spreading of manure. It covers storage. In some cases wherein you use sand bedding, it also covers separation of sand and manure. It requires nutrient management. It also looks at the impact of manure application on nutrients in the soil. It looks at runoff issues, and for some of the larger farms, they may be required to have nutrient management plans or certified nutrient management plans to provide a plan as well as record-keeping systems in terms of manure applications in their facility. It also provides for some energy efficiency opportunities. Together with manure, people have used manure, looked into anaerobic digester systems. I'm not going to go into depth of this, just wanted to mention this in general. ADs can help control odor, pathogen reduction, manure emission controls, liquid manure stabilization, as well as actually increase the amount of nutrients maintained in your manure that you can put on your fields. These are some of the gas yields, and just wanted to point out here that cattle manure has the least amount of gas productions among all the other potential feedstocks. So therefore, for cattle manure, you need a lot of manure to really equal the gains and value of gas productions from other feedstock sources. Here is an example of some of the data that's been provided for the amount of gas yields, the electricity generated, and the need of number of animals to produce 100 kilowatts. This is just for information purposes. what I'd like to, and also some general cost estimations that you may want to look at later. What I'd like to focus in this last few slides is basically looking at the manure pump agitators. A lot of the cost of the manure system is in the pumping of manure, the pumping of manure to other to tanks, or either the pumping of manure to as provide for irrigation to other parts of the field. Most manure pumping systems, especially in areas where you have single-phase electrical service, is done through PTO power by tractors or done through diesel-run generators. And given the high cost of diesel right now, it has become a very costly operation. So, what we'd like to do is look at the possibility of converting a diesel-powered manure system to that of an electrical system, okay? Now, there is one common assumption here, and the basic assumption is that you have three-phase electrical service to your farm, okay? That is one requirement at this point. I will mention some of the other aspects with regard to that, but for now, you can do these calculations by knowing two different things. If you know the hours of operation that your tractor is running to run your manure system, you can make that calculations. Another way is if you know the number of gallons used by your current manure pumping systems, we can also do that calculations. I will go through an example here for you. Okay, let's see that you know the number of hours that your tractor is being run to power your manure pumping systems. Now, you'll have to go to the following website here. There's a link on this presentation to look at the model, the make of your specific tractor, and get your fuel efficiency with regards to PTO. Now, the fuel efficiency of a tractor is different from the fuel efficiency of running its PTO as a tractor as a PTO source. So this website will give you that information. I have an example here of a John Deere 7320 diesel tractor, which has a PTO rating of around almost 110 horsepower and uses 6.7 gallons per hour diesel if the PTO is running that load, okay? And say you are using this tractor to run a equivalent of 40 horsepower manure pump. The closest table equivalent is around 48.7 horsepower per gallon at his price here was a 4 gallons per hour, okay? So first of all, this is the information that you can get from that website. Now, plugging in the numbers here, okay, we got an estimate of 864 gallons being used by this farm to pump manure at a price of diesel, farm price, I'm putting $3.75. So your total cost, just the fuel cost for pumping manure, we're not even considering the maintenance cost for the tractor, is $3,240, okay? So that is your actual cost. Now, if you're going to convert and use an electric motor to replace that power source, you use 364 gallons times what we call 12.5 water horsepower hour per gallon. Since there is no exact numbers for manure pumping, what we have used are the irrigation numbers from Nebraska. So by doing that and following the equations here, the equivalent of an electric motor pumping the same amount of volume that your tractor has is basically a cost of $1,000 $222 with an assumption of 10 cents per kilowatt hour, okay? So if you convert just on the fuel conversion itself, you have a savings of $2,020 on fuel savings by converting a manure system pump powered by PTO tractor to that of an equivalent of around a 40 horsepower electric motor, okay? The payback here is around three years, okay, with assumption of a 40 horsepower with variable frequency drive costing around $4,300, installation at $2,000. Total cost of this system is $6,300. So in this scenario, it makes sense to try to convert. But the basic problem here is you have to have a three-phase electrical service to your farm. Now, another method for doing pretty much coming up with the same results is presented on this next slide. It's a much simpler, easier way to do it. It is based on this table down here in terms of cost comparisons. All you have to do is saying I'm using 864 gallons total times the cost of the diesel at $3.75. You have your current cost. What you do is you $3.75 minus the equivalent of I'm using 10 cents per kilowatt hour. You go to this table, 10 cents per kilowatt hour is equivalent, go down the column here, is equivalent to $1.41 per gallon of diesel. So this is where I got the $1.41 here. Following this equation and this sample, you get pretty much the same numbers as of the previous method. So this is an example of terms of giving a quick calculation, just fuel cost as well as the cost of an electric motor and installation to see if it is worth it for you. Here is a table in which gives you in general conversion rates for fuel comparison. Basically natural gas, well, this is the electricity rate right now that I'm comparing it with, and you can compare it with diesel, propane, and so forth. Issues faced with single-phase service. There's great potential for energy efficiency improvement opportunities for agricultural operations. However, lack of access to three-phase electrical power has often limited agricultural productivity and energy efficiency options for a great majority of farms. This is particularly evident in the inability to use large, energy-efficient electrical motors in lieu of less efficient diesel motors or PTO-powered systems. The result often leads to limiting farm operations like manure pumping and irrigation below optimal levels due to high costs of diesel fuel or incurring high energy costs in manure operations that wipe out profits. Grain drying, feed operations, fruit vegetable refrigeration, biodigestion, and biomass processing also face these limitations in a single-phase environment. For manure and irrigation operations, the equivalent cost of, let's say, 12 cents per kilowatt hour of electricity is around $1.80 per gallon of diesel. The example I had was 10 cents per kilowatt hour, which is equivalent to around $1.41 per diesel. Attempts to solve this problem include installing three-phase service, if available, and the cost that utility companies are giving or will be spending, some of them have funding to do this, is around $50,000 per mile. That is a huge amount. And as well as installation in your facility of around $10,000. So it is very costly. Another option would be install a three-phase converter system coupled with soft start motors. Though this allows the use of more efficient and less costly three-phase motors, the issue of undesirable voltage drop caused by startup current requirements of large electric motors still limits motor size to around 10 or 12 horsepower. So you still, even though you have a phase converter, you still can't be using large electrical motors. Or else your neighbors will be complaining because of flickering. Another option that some farmers are starting to use right now is the use of large written pole motors. They are not widely used right now due to concerns by utility companies regarding inrush current demands. But I have heard, in fact, we have 3 of those operating here in Michigan, and the utility companies that those farms are under so far have not complained. So we're keeping our fingers crossed that they may be a solution. I'm including other slides with some other fuel conversion cost data for your use, and if you need to refer to them, this is just for reference. And I have some more slides here for you for your reference, as well as some of the wood and other sources. And I've included the reference in which we used for this presentation. And that's the end of my presentations, and hopefully some of you have questions. I guess I put them to sleep already. Scott?
Oh, I see one from Mark. Hang on a minute. I had one. I'm looking this one up. The fuel conversions you've had. Does that account for efficiency differences between an electric motor and a gas motor? That table you
No, that's an added factor that would benefit converting to an electric motor. This is just fuel cost, totally just fuel cost.
Yeah, but in that fuel cost, so that's just looking at the energy content of...
the table that was done there has embedded into it some of the energy efficiency assumptions there. And that table comes from the University of Nebraska studies in terms of conversion from diesel to electric motors. So there is some embedded aspects to that. But I believe we're given the even higher efficiency motors that we're having right now. The assumption of the motors that were used in making that data was around 90% efficiency.
Mm-hmm.
So with even the higher efficiency of electric motors going into 94, 95, and even the super high efficiency motors going at 96%, the meter will even tend better towards the electrical motors.
Okay, we've got a comment from Mark Hanna. It says, your conversion from nitrogen to diesel seems a lot higher than I've ever seen.
Okay, I got the result there from the Iowa study. I can bring it up. That was kind of the rule of thumb. That includes all the manufacturing costs, if from
yeah, but I think he thinks that you got it reversed. He thinks it's 4 to 5 pounds of N per gallon of diesel, rather than the other way around.
It could be. I just used the data I got from that, but they broke it down. They broke down the 5 gallon diesel in terms of how much from the refining, the processing, transportation, and so forth. So I didn't show the breakdown of that 5 gallons. I just used the 5 gallons that study used. It could be higher, but
no, I think it's a reverse number.
It could be reversed, but
because as I remember,
that was just the data I used. There'd be other sources that have a different resource. So
yeah, because Mark and I did Mark did a presentation earlier, and I actually looked up the numbers because I was doing some work too, and it.
Yeah, I could send the study that Iowa did on this, and
yeah, it was about 120 pounds of N would equal about 20 gallons of diesel, in that range. So.
Correct. I would agree with that. But this study started the cost of production from crude.
Well, that's what this was using.
Same thing? Okay.
So.
Okay. Okay.
Any other questions? All right, I don't see any or hear any. So I think we'll call it a day and remind people that if you're interested on grain drying, that happens on next Tuesday with Ken Halvang. Otherwise, I'd like to thank Al for his time and putting this together, and I'll be sending out a post-evaluation here shortly. Thank you.